Okay. Before we get going today, let's talk about how we're going to wrap things up. Okay. Now, I do have your research paper in. Thank you very much. I have Lauren's in. Thank her very much. I'm still waiting for Bailey's. Thank you very much. Okay. First test, have I returned to you?
No.
I didn't?
Great,
Well, I should have returned them to you. Let me get those back to you. I think I just recently got the last one in, so I thought I returned them, but maybe not. Oh, I know what I was doing. I was looking at Cal 1. Okay, here we go. That's one. See, it shows up in this test. Okay. Let's see, test 2. Test 2. Test 2. A whole line of blanks under that. Don't understand that at all. Okay. Need those in, preferably. Like to have had them before Wednesday, but whenever you can get them to me, get them to me. Okay. All right, and then I'll be giving you test 3 on Wednesday. Okay? So what we're going to do from now is continue in chapter 8, 8.3, and we're going to wrap up hopefully today, center of mass. Okay? We're not going to do 8.4. I highly recommend you look at it. It's a really powerful tool, and but we just don't have time to do it. Chapter 9, differential equations, which is another course, so we're not going to do that. So we're going to move on to chapter 10, infinite series, and get as much of that done today as we can too. And we'll continue that on Wednesday. Okay. I will pass out to you on Wednesday your last test, and I really won't know until the end of class on Wednesday how far we get. So I'll let you know how many questions will be optional and how many will be required on that last test. Okay, good deal. Any questions? I do need that second test in, though, right? Okay, good deal. All right, where we left off in center of mass was example 1, and I believe this is the figure for example 1. So let's see if I can blow this up. Boom, there it is. Okay, it says find the center of mass of the system of 3 particles in this figure. Okay, here's 1, here's 1, and here's 1. Those 3 particles. Now they show where the center of mass is, sort of ignore that for now. Okay? Yeah, I thought I must have bad breath or something that you decided to sit way back there. Okay. I know, I'm just kidding. Well, if I can give you a hard time, I like it. Okay. All right. Good deal. Okay, so find the center of mass of the system of 3 particles having masses of 2, 4, and 8. So those numbers represent the masses of the particles, and you see the location. 2 is at 0, 2, 4 is at 3, 1, and 8 is at 6, 4. Okay? Now, how do we do center of mass? What's the basic formula for that? Say again? Okay, you want to start with X bar. Let me get my pen activated. Okay, so X bar, how do you define X bar? Or bar X, if you want to call it that. Out west, we call it the bar X ranch. Okay, never mind. Okay, never mind. M1x1 plus M2x2 plus M3x3, all divided by M1 plus M2 plus M3. 3. I mean, when you write it this way, it almost looks like it makes sense, okay? That you're adding the products together and dividing by the masses, and that gives you the x's. You know, that really is what it looks like. That's not what it's doing. That's algebraically not correct, but that is a real good, to me, mental crutch to make sure, yeah, I'm doing it right, okay? So we're doing the x values and the mass values. So what's your M1 for object 1? Here it is. What's the mass? Those numbers are the mass.
4 and 8.
Yeah, 2, 4, and 8.
So you add them all?
No, wait. Yeah, we will eventually. Let's just do as we're going. M1 is 2, right? And what's the x1 value of 2? What's the x value of that position? 0. So that's 2 times 0. I think I can even handle that one. Plus 4 times 3 plus 8 times 6. Okay, divided by, now you get to add them up. 14. All right. And what would that be then? That goes to 0. I'll take care of the first one. Okay. You get 12 plus, what again? Big numbers, huh? 48 over 14. 12 plus 48 is 60 over 14, which would be 30 over 7. Okay? Real nice number. Okay? That's your x bar. The y bar would be what then? Oh, just based on what we just did. M1. Y1. All right. Yeah, we already know what it is. Let's just write down 14. Okay? You could write it all again if you want to. No, you're having me doing the writing. You want me to write it all out. You want me to do all the work. Okay? Thank you very much. I'll remember that. Okay? So, what's M1, Y1?
2 times 2.
2, got it. Big numbers, okay?
4 times 1.
Got it.
8 times 4.
All over. Okay. And what's that?
4 plus 4 plus 32.
Which is over 14. And that would be 40 over 14, which would be 20 over 7. So we got 30 over 7 for our x bar and 20 over 7 for our y bar. Let's get approximately what that is. 30 over 7 is just a little bit more than 4, right? Okay. So it's a little bit past 4. Yeah, that's looking pretty good. And 20 over 7 is just short of 3, right? Yeah, that's looking pretty good. There's the center of mass for those 3 objects. Does that really look like the center? Looks like to me it's closer to 8 than it is to 2 or 4, isn't it?
Well, I mean,
yeah, but 8's heavier. You're right. That's pulling it that way. Yeah. Remember the seesaw and the football player? Yeah. You have to get closer to the football player to get that center of mass right. Okay. Good deal. I'd rather get closer to ballerina. No, come on. We won't go there. Okay. It's not that funny. Okay. All right. See how to do that. Got it? All right. Good deal. That's example 1. Let's move on to, whoa, they're moving pretty fast here. They mention a thing, and they have already mentioned it, a thing called a lamina, okay, which is a thin plate. Okay, they got the slides out of order, okay. So what a lamina is a thin plate. Consider a lamina, thin plate of a constant mass density. All right, this is going to simplify things big time. If you have something that's varying in density as you go, then you've got a real big problem on your hand. But if you can express that density as a function of x, y, or x, y, and z, then you can still do it, okay? Much simpler if it's uniform density, so that there's no variation in space with the density, okay? So the mass density, the symbol for that is usually given as a little symbol delta. We're used to capital delta, that's the triangle-looking thing. Little delta is like that, okay? And that's typically the symbol for density, okay, mass density. And we're going to assume that's a constant. Occupying a region under the graph of F over an interval from A to B, okay? Where, F is continuous and F of X is always greater than or equal to 0. So that's what this is showing us here. Here's your function, y is equal to f of x, right? Okay, it's always greater than 0 on this interval from A to B, x going from A to B, and we're going to assume everything is uniform under here. Okay, obviously it looks like it's going south of this, but you see we're not going that far, okay? So we're just considering that plate there. A lamina occupying the region under the graph of f of x over A to B, okay? And you want f of x to always stay positive, okay? Now, okay, in our calculations we'll use the principles of additivity of moments mentioned above for the point masses. If a region, oh, he did decide to show up today. One was saying you weren't coming, that you didn't want to mess with us anymore, and that you had nothing to do with us. So, you were wrong, weren't you? Okay. I just.
This week alive, it'll be a success. There's so much going on.
Is it schoolwork or also?
Yeah.
Okay.
Because I had like the blood bowl 2 weeks ago, and now it's all physical. Now it's
All
all
mental. Okay. Which is easy. I won't ask that question. Okay. How was the giving blood?
Tomorrow.
Oh, is it? No wonder you're grinning. Okay, you're looking forward to it. All right, good deal. Okay. You do it there on campus, or you go to the Red Cross? Or
I'm not sure.
you do what they tell you to.
They tell me.
All right. How's progress on the paper?
I actually started it, but
Yeah.
I also got, last night I had to finish my
Yeah.
engineering project.
Right.
So, but I should have it done by tonight.
Okay.
Do you want me to bring a paper copy or email it?
That's up to you. Let me, I always get that question, several times a term. Let me explain my answer. I grade what I receive, okay? And I've received some email copies. The vast majority of the time, email copies I receive are fine, perfectly fine. But I have received some email copies before that have been so screwed up, and I can't believe the person sent them that way, but maybe they just didn't even look at them carefully and didn't have their formatting done well, or other stuff like that. Like they had everything center justified rather than left justified, and stuff like that. And maybe they did it, or maybe it got screwed up when they sent it. I don't know, but I have to grade what I receive. So it's up to you. If you're confident you're sending me a good, clean copy, that's what I'll grade. But if you want to make sure this is what I want him grading, then so do it either way. I don't care much. Okay, so I want to give you as good a grade as possible, but yeah, that's up to you. Okay, what we're doing is on page 458, chapter 8, further application of integral and Taylor polynomials. We're not going to do the Taylor polynomials. We're doing center of mass. We finished example 1, and we're talking about lamina. And where we left off is just that first italicized region right under that first paragraph. If a region is decomposed into smaller, non-overlapping regions, then the moment and the region is the sum of the moments of the smaller regions. Not the sum of the center of masses, but the sum of the moments, okay? And that's why they like moments, and that's why engineering uses moments. Just as soon avoid moments because they almost are confusing to read, but that's an advantage to them. To compute the moment with respect to the x-axis, m sub y, with respect to the y-axis, m sub x, you do your masses times your x's, not times the y's, okay? It's with respect to the y. We begin, as usual, by dividing AB into n sub-intervals of width delta x, okay? So that's what we're getting to in the next one, okay? If that's the region we're looking at, okay, and you're you want the other one now? Keep them together so I don't lose them. Okay. And you haven't started this one, right? Okay. I know you don't want the answer key, so that's test 2.
Thank you.
The other guy's still working on his?
Yes.
Okay. All right. So what we're doing here is doing the moment with respect to the y-axis, m sub y. Okay? So here's the assumptions here. Let's go back. You weren't anywhere when we mentioned this. What we're saying is this is a thin laminar plate that's uniform density. That's why the delta's up there. That's what stands for density. It's constant through this. It's not getting denser as you go here or here, or varying density in between. It's a constant density. So if it is a constant density, then you can take each individual strip, because this strip is approximately the same distance from the y-axis. The x value is all the same here, right? So you take the strips and you do your, the mass of this strip times the distance from the y-axis. So it's M1, X1, just like we did before. One would remind you of that if you looked at, right? M1, X1. We do this strip plus that strip plus this strip, all like this. So that's the J strip there that we're doing. M sub J. Now what's the M sub J? Well, the mass is your density, and this is a area density, so it's length times width times density, right? If the density, that delta, is mass per unit area, then multiply that by area. The area would be alpha of x, right? Alpha of x of j times delta x of j, right? That's your area. And multiply that by the density, and you get your mass, okay? So you've got delta alpha of x dx, basically. Okay, times x. Okay, that's how far you are from the y-axis. Okay, just like before, that was 1, 3, 7, whatever it was. You're just x units from that. So that's your x of j. So now your moment, they like to call it that, but the sum of your products of your masses times your distance in the x direction, that would be alpha of x dx times your delta times x. So it's x alpha of x dx times delta. Okay, that's each of these shaded strips, and then we're going to sum those up, add them together, and that's what we were saying before, adding those moments together, and that gives you the total moment that you have. Okay? So the area is f of x delta x, that's what we just said. The distance is x, and then your delta is your delta. Okay. I had that blown up, but then. So here's your moment with respect to the y-axis, which I like to think of in the x direction, okay? They like to say with respect to the y-axis. Okay, now, your text is calling the density delta. Their text, the previous one, is calling it rho. It doesn't matter what you call it, that's the density. Okay, sorry that they changed the symbols here. In ours, the newer edition, this is a delta, not a rho. Whoa, but I can't write on that, I forgot. Okay, so since I do need to write on it, then let me get out of it and write on it like this. So that's now a delta in your edition. And that moment is the integral from a to b, divided into the x's. X was your distance, f of x was the height, dx is the width, and the delta times the f of x dx, that gives you the mass times the distance. That's your moment, okay, with respect to the y-axis. I like to think of this, the moment in the x direction. But it's with respect to y. Okay. Now, and what was your center of mass? The moment divided by the total mass. Okay? So the total mass then, I'll blow this up for now. Boom. Okay. Oh, I'm sorry. This is m sub y again. I don't know why they've written it again. Okay. M sub y is your delta, rho, whatever you want to call it. The integral from this, the length I was going to say x is not the length of the vertical. It's x, that's the distance from the y-axis, your x displacement, times the length of the vertical cut, which is your, okay. Sorry, now I know what they're doing. They've got the slides all screwed up. Okay. Where they went here, okay, sorry about this. Let me go back a few slides. Remember this slide? I said they got it out of order. This is now when you have your mass here that is between two curves, F1 and F2. For F1, it's always greater than or equal to F2. So you're not doing it to the x-axis, you're doing it here. Well, now your length here is your F1 minus F2. Remember, F1 is always greater than or equal to F2, so it's F1 minus F2 times dx times your x. So there's the same thing we did before, except we have the length is now not just f of x, it's f1 of x minus f2 of x. So that's what they were doing in this one, okay. The length of the vertical thing, and that's where the f1 minus f2 came from. So whichever way you have it, whether it's just with the x-axis or between two graphs, this would be it for that. Okay. And that's still only dealing with the moments. Now, what if you had the graphs like this? You're between two this way. Now you do your moment with respect to the x-axis, and the distance here is y. The length is the difference between these. And in this one, they made G1, okay, they have G1 the further one and G2 the lesser one, which sort of seems backwards to me, but however they call it, G1 minus G2, that's the length, dy is your thickness, the delta is your density, and you're integrating from C to D, okay, along that way. Okay. So here's that expression. Finish?
Yes, sir.
You said you had already done the second test.
Yes, sir, I got it.
Appreciate it. All right. So here's your m of x here. M sub x is the moment with respect to the x-axis, which is with, from the y, along y is how I like to say it. Your density, and again, that's going to be delta in your u addition. The integral from c to d, these are the values on y, so you're doing a dy. The distance from the x-axis is y. The length is the difference between g1 of x and g2 of x, and then your thickness is dy. Same type deal with that. All right. Now, what do you do with all that? That gives you your moments. What you have to do is get your mass as your denominator. And what is your mass as a denominator? That's even simpler. Okay? I think before... Okay. Let me go on and rewrite these as deltas. Okay? That's not a very pretty delta. Okay? Now let's blow them up. Rather than... Okay. So what is your mass? Your density times the area. What's the area? It's your length times your width. Okay? The summation of the length times the width from A to B times your density. They were using rows, and they now use delta. Whatever. This is if you're doing with respect to x, two functions like this, or with respect to y, two functions like that. That's your length there. Your dy is thickness that way. Okay. So that gives you that. Now, your center of mass, and let me correct this too, as one was saying, bar x or x bar, okay, that's the more common, perhaps nowadays. They don't use cm, but occasionally you will see cm. You'll even see COM, center of mass, but the newer text uses this. So your x bar, now I'll blow it up, is your moment with respect to y, which is distance from the x-axis. Okay, that's what your y is, divided by the mass, and your x. Y bar is the distance, is the moment with respect to the x-axis, which is mass times distances from the x-axis. Okay, from in the y direction, and that's your mass divided by m. Okay. Now, I think we're ready for example 2. I think this is it. I was going to see if they have this other one. I don't guess they show the other figure. Oops. Okay. So let's do example 2. Find the moments and the center of mass of the lamina of uniform density delta occupying a region underneath the graph f of x is equal to x squared and above the x-axis for 0 less than x less than or equal to 2. So there is your, sorry, here's your picture, okay? Is there anything I need to, I don't guess I do, okay. They haven't written it on here, but we're assuming uniform density, okay, whatever it is. So here's your function, y is equal to f of x, which is x squared, okay? Now, if you're doing your x bar, okay, then you're summing this. Think of it in 2 steps here, Okay? I can't write on this, I keep forgetting. Okay? Now this is the region under the parabola, not inside the parabola. Okay? It's underneath the parabola. Okay? As shown there. So let's get out of that. So let's do the dx's first. Okay, there's your dx. Okay, here is your f of x, x squared, and your they like to call it m sub y, so I'll call it m sub y is equal to your delta, which is your density, uniform density, so we can, as you'll see, we're going to throw it away. We don't ever use it. We don't really need to know it, but it's in the picture, times the integral from, what's your x going from? 0 to 2, okay? And then your, the mass is your density times the area. What's your area? Okay, length times width. The length will be your y, which is x squared, and your width is dx. Okay? Okay, so that's your area part. But your distance part, okay, and area times density is mass, and then the distance here is x. That's how far you are from the y-axis. So you have another x in there. So this brings it up to an x cubed then. Do you see that? X times f of x. Okay? Now, that's going to be fairly straightforward to do. That's going to be your density rho. And what's the antiderivative of x cubed? Over. Yeah, that, okay, yeah. Over 4, evaluated from 0 to 2, and that will be 2 to the 4th is that's 5th. 16. 16 divided by 4 is 4. So this is going to be 4 delta, because 0, is 0. Okay. So that's your m sub y. Now, to do the m sub x, now we need to do the dy's, not dx's. Okay? So I'm going to erase, just so it won't be in the way here. Okay? We have to now deal with a dy here. Okay? Now, your delta is still delta. Okay? That doesn't change. What is your y going to? So if you're doing dy's here, y is going from 0 to 4. Okay? Now, your dy is the thickness of that. Your y is the distance from that, so you're going to have a y in there too. Now what we have to do is get the length of this. And the length of this is the right-hand endpoint minus the left-hand endpoint. Well, and you want this in terms of y. Well, if this is y is equal to x squared, that's the same as saying x is equal to the square root of y, right? So this curve right here is the square root of y, so it's 2 minus the square root of y. That's the length of that, right? The right minus left. Greater minus less. Okay? So it's 2 minus the square root of y. So that's going to be your, and can I write that rather than square root as something else? Y to the 1/2, right? Not negative 1/2. Okay, that's how far you are. Remember, what you're doing is mass times distance. Okay, and you're doing this with respect to the x-axis. So the distance from the x-axis is your y, and the mass is your length times width. Length is 2 minus square root of y times dy. Right? That answer it? Okay. Now, a little bit more involved in this one. That's your delta going from 0 to 4. And let's distribute that y. What do you get there? 2y minus y to the 3 halves. Very good. dy. Okay, let's integrate that. The delta's there. Antiderivative of 2y is? Wow, that's fast.
Yeah, I got study mode.
Okay. Okay, that's going to be y squared minus a little louder. Y to the 5 halves multiplied by 2/5. Is that what you're saying? Yeah, that's what I like to say too. Okay. And that's evaluated from 0 to 4. I can't read my 4, but you got it. Okay. And this will be the delta. Okay, when you plug in a 4 there, what do you get? (16) minus. Now, what I like to do is take the square root first. So let's do the square root of 4 is to the 5th is 2, okay? And then multiply that by 2, that would be 64, divided by 5, that would be 64 fifths, right? Okay. I think that's what we got. Minus 64 fifths. Think that's what it is? I think that's right. Okay. What is that? That's delta times, what's 5 times 16? 80 minus 64 fifths. You buy that? Calculators slow you down a little bit, don't they? Okay. That's equal to delta times 16 fifths. Is that right? All right. So that's your moment with respect to the x-axis. One other piece of information we need before we can go to our center of masses, the x and y coordinates. Basically, you got your numerators. What's going to go in the denominator? The total mass. So the total mass is your delta, as always, times, and this, let's go back to the easy one, okay? Let's do it dx, because the mass is a mass, right? So that's going to be from 0 to 2 again. We're going to do our dx's here, okay? And that's just going to be length times width. And your length is x squared, and your width is dx, right? You buy that? Why not? I mean, you could do it the other way. Just pick one. To me, this is easier. You might like your fractional exponents. You probably do. Yeah, you're that way, aren't you? Yeah. It's just like we did before, only we don't have the extra x in here this way. It's the length times the width. The width is dx, and the height is x squared. Right? That curve, the y there is x squared. Y is equal to f over x. But, yeah. What's that? That's your width. Length times width is your area times density, which is mass per unit area, sum it from 0 to 2. You do this little rectangle. Wipe out the other rectangle so it won't be confusing. Okay. You're doing the total area under this curve. And that total area under the curve, if you do a dx down here, that's going to be the width. The height is going to be your f of x, the curve here, which is x squared, right? So height times width is x squared times dx. Sum that from 0 to 2. X squared times dx. Sum from 0 to 2. Multiply that by the distance. Got it? Still fuzzy?
Just because on what we just did, the reason there's two parts is because there's another graph. Is that why?
Okay. It's the same graph.
Okay. There's another line that you're going this way.
Okay.
So you're not stuck with the axis.
Okay. Yeah. For the moment, you also are worrying about how far from the axis you are. So this first one up here is how far you are from the y-axis. That's the moment with respect to the y. Is that mass times how far you are from that, right? It's your mass times the x displacement of the mass, right? Which is how far from the y-axis you are. So that's why you had the extra x in here. And on this one, you're having to go this way. So now you're having to do your mass. Now your mass here is that horizontal strip. And that is your length times your thickness, which is your dy. And then you multiply that by how far you are from the x-axis, right? So that's your imps of x. This was your imps of y. The mass, just do either one of them, which is the easiest to do. All you're doing is length times width. And you could have done this length times width and just done that. But don't worry about how far you are from the x-axis. Don't worry about how far you're just summing all those rectangles together. And to me, this is the easier one to do than to do that. To do it that way, it'll get the same answer. But this is the easier one to do. So I'm lazy. I go the easy way. Does that make sense? Yeah. Okay. So this is your denominator. These are your two numerators. That's the denominator for both. And what does that come out being? Antiderivative of x squared. Second. All right, x cubed over 3, evaluated from 0 to 2, right? And that would be delta times, a little louder? I don't think so. 2 cubed is 8 divided by 3, right? All right, 8/3, okay. Now, so that's your denominator for both of them. So, your x bar is this m sub y, the moment with respect to y, which is the thing multiplied by x, okay? And that came out being 4 delta over your mass, which is 8/3 delta. Look what happens to your deltas. They divide out. That's why I said it really doesn't matter what the density is, as long as it's uniform. And 4 divided by 8/3 would be 3/2. Okay? Does that make sense? Let's do the y bar. That is your m sub x, which we found to be 16/5 delta divided by 8/3 delta. And again, the deltas are gone. And 8 will go into 16 twice, so that would be 6/5. Okay? So let's see if that kind of makes sense. 0 to 2 is, there's 1. Get those sticking lines out of the way. Okay. All right. Okay. So your X bar is going to be, here's 2, there's 1, 1.5. So it's going to be somewhere about here. And your Y bar is going to be 6/5, just a little bit more than 1. So if this is 4, that would be 2, that would be 1, a little bit past 1. So it's going to be somewhere right about in there. Does that look like that could be about the center of mass? See, you got a lot up here, a little here, so it's going to be closer down here. You got more here than you do up there. So it's going to be closer here, but you got more over here than you do over here, so it's going to be closer that way. Sure enough, that looks pretty reasonable. 3/2, 6/5. Let's see what they got. X bar is 3/2, Y bar 6/5. Let's see if they have that next figure. No, they don't. In your book, they show the center of mass there. 3/2, 6/5. The center of mass of a lamina with a constant mass density rho is also called the centroid. I always have trouble with that word because I have to take thyroid medicine, and it's a synthetic thyroid medicine, and that's called Synthroid. And this is centroid, okay? So I'll sometimes say them backwards, okay? So anyway, this is a centroid. The centroid depends on the shape of the lamina, but not on its mass density, because the mass density is uniform. So they divide out. They're not in play anymore, okay? In particular, in calculating the centroid, we can take delta equal to 1 and not even mess with it anymore. You don't have to carry it around and then divide it off away. The drawback for that is that it requires integration along the y-axis. Oh, this is for mx. It requires integration along the y-axis, which may cause difficulties if the lamina is defined in terms of functions of x, and they're not easily changed. Like this one, x squared can be written as y to the 1/2, right? So that was easy to do. There could be some that are very, very difficult, okay? Well, if you have that being the case, here is the other way you could do it. If you have this y, let me blow this up a little bit. If your y is a function of x, and it's not something that's real easy to go back and then do an inverse of it and say x is a function of y, because that may be a really complicated function that's not easily invertible. Okay. Well, here's what you can do in that case. Rather than doing dy's like we did before, okay, because then you have to get, and you see this would be really ugly here, because see, here your dy's would be going from B to A. That would be easy. But here they would be going from B to F inverse of this. And here it would be doing from this to that, which would be really a mess. Okay? So yeah, we don't want to do that. So here's the alternative way to do it. Keeping our dx's here, because we've got y as a function of x, keeping everything in dx's, let's do the center of mass of each strip. Okay? The center of mass of each strip would be halfway up that strip, because it's uniform density, right? And uniform thickness, uniform everything. So it would be halfway. So we know what that would be. Well, that would be 1/2 of f of x. Okay? And then your f of x would be your height, and dx is your thickness. So you have really 1/2 times f of x. That would be 1/2 f squared of x. Okay, and then you do it that way as approximate height of that. Okay, and then you sum those up and you get them that way. It's a little messier algebraically, but it's certainly cleaner doing integrals. Okay, much cleaner doing the integrals. And yeah, I think that's all we need to say about it. Then all your integrations are dx's. You don't have to worry with the dy's. The dy's worked only if it's real easy to do the inverse function. All right, so here's what it would look like then, in this case. If you did it that way we just described with that last illustration, okay, your m sub x, your moment with respect to the x-axis, that would be your y value, the 1/2, remember it was 1/2 alpha of x times alpha of x. Pull the 1/2 in your density, they're giving rho, but it would be a delta in our book, okay? Integral from a to b, alpha squared of x dx. 1 alpha of x is from the 1/2 alpha of x, that's halfway up the thing. The other alpha of x is the top, the length of that, okay? dx, that's your thickness of that. Now, what if you're going between two functions, though, not from the x-axis, okay? Now, here is a little bit, I wish they had an illustration of this. I don't think they do. Let me see if they do. I don't think they do. No. Let me go back to this one. Okay. Let me impose. What if you had some other function down here? It's not going to the bottom. Okay? So you have a F, what do they call it? F1 of x up here and F2 of x down here. Right? Now, your alpha of x, your length is still going to be F1 minus F2, right? Your dx is still dx, right? But your midpoint here is going to be the average of these two, which is F1 of x plus F2 of x divided by 2, right? By that? Okay. No. All right. So that's going to be, then you have the sum of these two divided by 2 is your average. The difference of these two is your length. Well, sometimes the difference would give you F1 squared minus F2 squared, right? F1 plus F2 times F1 minus F2 is F1. This is squared. Right. 1/2 because one of those from the average one. So that's where that came from. They sort of just threw it in here without really a good explanation of where that came from. But that's where it comes from. Okay? So that's actually winds up being, I think, the easier way to do it than having to turn around and do y as a function of that, or x as a function of y. If it works out that way, fine, do it. Okay. So I think we're then ready for example 3. And example 3, I believe, is this one. All right. Find the centroid of the shaded region in this figure. In your new book, it's figure 14, because they've had a couple more figures they didn't show. In the old, it was figure 11, but it's the same figure. Okay? It's y is equal to e to the x from 1 to 3. The centroid does not depend on the delta, so we can set delta equal 1 or just forget about it, basically, and apply the equations without the delta in it, or just ignore the delta. Okay? Now, so let's do it. Let's do this as our delta x, or dx. Okay? What would be the centroid of that? let's do moment with respect to the y-axis first. Okay, so that's going to be this one. What would that be? Take it. Go ahead. You can do it in harmony. I don't care. Okay. Okay. Okay, we'll have the delta in there. Integral from 1 to 3, is that what you said? Okay, I thought so. Okay. Okay, you said, yeah, x times e to the x, is that what you said? Okay, e to the x times dx. Perfect. Okay? For that strip is x units from here, so that's your length. This is from the y-axis, that's m to y, is the x, going from 1 to 3, okay? Times the height, which is e to the x, times the thickness, which is dx. So that's perfect. Now remember, we're saying uniform density, so let's just make that delta 1. So we don't have to carry around the deltas anymore. Just have it as a 1. So I just want to get rid of it. I'm tired of writing it. Okay. It's ugly. Okay. All right. And let's do that. Ooh, wow. Can we do that? How? Second? I think not. I think not. Okay. Huh? Okay. And that is, how do you do it? Think you've got a product there. Which one of our techniques dealt with a product issue? By parts, exactly. Okay? So what parts is parts? Let what? Let EX? Okay, let's let X. Well, let's name. It's almost like a substitution, but not quite. We're going to give some new names to it. And what are our favorite names? U, okay. Let U equal which one? X. And dV equal e to the x dx. Yeah, you got to keep your d's together, right? So then, what's du is equal to dx, 1 dx, okay? And v would be equal to e to the x. You got it, okay? Integration by parts tells us what do we do next? Okay, I see. He's conducting a band. Okay. Is that how your catcher sends you signals? Okay. What would you do if he did? Throw whatever you want. Okay. U times V, so this would be x e to the x. Oh, you said minus? Okay, minus. Of the bottom line here. And what would that be? E to the x dx. Okay? So, and this, by the way, is also evaluated from 1 to 3. That first part, you evaluate that 1 to 3. Okay? So let's do that first evaluation. What would that be? 3 e to the third minus e. E, okay. Minus, and what's you got there? E to the x evaluated from 1 to 3. So this will be 3e to the 3 minus e, and what would this be? A little louder. How did you get that? E to the third minus a minus, which would be plus e, right? Yay or nay? Okay, and the plus e minus e messes up, okay? And this just leaves you 2e cubed. You buy that? All right, so that's the m sub y, which is the kind of the middle easy one. It's not as easy as m, but it may be a little bit easier than m sub x. So what do you want to do next? M sub x. Let's try m sub x. Now, what is m sub x? How does that go? And remember, our delta we're going to count as 1, so we're not going to mess with that. So what are we going to do for m sub x? Integral. Okay. You say 0 to 25. Okay, he's trusting that this thing is drawn really poorly. Okay, it's not going to 25. Okay, let's do our alternate way. Now, what we could do is x is equal to log y, maybe. If you wanted to do that, do you really want to do that? Huh? So I don't really want to either. Let's take our midpoint. Remember? We're going to do the midpoint. We'll do it this way, the second way we did it. And there, part of the integration is almost the same. Not quite. What would this be then? Say again? You may have said it, I just couldn't understand.
0 to 25
Okay, I'm sorry.
0 to 25
He's wanting to do that too. Y'all are in cahoots against me today, aren't you? Okay. No, let's keep it dx. Keep it simple. Okay. We're going to keep the dx. See, that's the same length, width. I mean, everything's the same. That's the same dx there. So this is going from 1 to 3 still. That doesn't change. And your area doesn't change. Your dx is the thickness. Your e to the x is your height. That stays the same. But what is different about this one? Say again? No, the width is still dx. And the height is still e to the x. So that part's the same. But what we're doing here is what? Midpoint, which is 1/2 of e to the x. So that's why I left a space here to put the 1/2 there, and that would be e to the 2x then, wouldn't it? Yay or nay? Okay. That work? Okay. Now let's see what that yields us. 1/2. What's the antiderivative of e to the 2x? Oh, yeah, you could. Okay, let's do that. I don't want to stifle your creativity here. Okay, so what would be your substitution? To what? 2x, I like it. Then du is equal to? A little louder? 2dx. Okay, perfect. Okay, but we really don't have a 2dx. We have a dx. So let's divide everything by 2. So that gives you dx is equal to du over 2, 1/2 du. So we pull another 1/2 out, okay, and that would be a 1/4 integral. Okay, now if u is 2x, x is going from 1 to 3, what's u going from? Two to six. 2 to 6. And what do you have there? E to the u du, because we already took out the 1/2 in front, so yeah. Okay, I think we can handle that. What does this give us? 1/4. Say again? E to the u, evaluated from 2 to 6, which would be say again? E to the 6, is that what you said? Yeah, okay. With a lot of confidence, okay? Yeah, or minus, or divided, or multiplied. E to the what? 2 over 4. By that? Okay? So that's your m sub x. Got one more to do. And I don't know if you want to do this or not. You could write this as e squared times e to the 4th minus 1 over 4. I don't know if that helps make it any better or not, but that's true, isn't it? So I don't know if that makes it better or not. But either way, okay. What else do you need to do? Your m. Okay, and what's your m? Say again? It's the mass, yes. And how do you get it? Okay, this time, say again? Yeah, let's do our same delta x there. And this time it's just integral from, yeah, from 1 to 3 e to the x dx. Height times width. Nothing extra, nothing added, nothing multiplied, nothing halved or anything else, just that. And what does that give us? To evaluate it from, which would be e to the 3rd minus e. Right? Okay. So, all this, and let's do first our x bar. That's your m sub y, which was this thing, right? 2e cubed over e cubed minus e, right? And your y bar would be, I don't know which one's going to be any better or worse. I don't think it really matters. So we'll just, let's try it this way first. E squared times e to the 4th minus 1 over 4 over e times e squared minus 1. Is that okay? I guess I could have done that. Yeah, let's do that up here too. This would be 2e cubed over e to the e squared minus 1. Right? And that way you can get an e to go out, and that gives you 2, I'm sorry, it's getting really crowded here, 2e squared over e squared minus 1. Okay. That may be the easier way to write that one. And down here, we'll cancel out an e. And what you can also do here is e fourth minus 1 is e squared plus 1 times e squared minus 1, right? And the e squared minus 1's go out, and that leaves us e over 4 times e squared plus 1. Now, I don't know if that's the simplest way to write the answer or not. Let's see what they got. Okay, they left it fairly complicated. Okay, fine. Their x bar was 2e cubed over e cubed minus e, exactly like we left it, our first answer. And our y bar was basically what we wrote down first, e6 minus e squared over 4 times yeah, 4 times e cubed minus e1, yeah. Before I started fiddling around with it. And then you can plug in your values. If you have any doubts that we have the same answer, which you may really have doubts on this, because it's so sort of screwed up right now. But if you got your calculator, are you plugging that in right now?
Yeah, I did the first one.
You did the first one? You got the same answer? Hopefully. You did. And then you can do the second one. I think you'll get the same answer. Okay. I thought it would simplify things. They just left it sort of complicated and plugged in the values. Okay. Now, that was getting a little, it was pretty, I mean, just do the stuff, right? The calculations may get a little messy, but you're just doing the same stuff. Now, here's a place where things can get easier. Now, again, we're assuming you're dealing with lamina, okay, centroids, not variable densities, uniform density. If you have something that's symmetric here, it's the same on the left as it is on the right, then you know the center of mass has got to be in the middle, okay, between the left and right. Now, if you had the same thing top and bottom, then it has to be in the middle of that too. But we don't have that. We have same thing here, so we know we have to. You don't have to even worry with figuring out what x bar is. X bar is 0. Okay, it has to be because it's exactly symmetric. Y bar you have to figure out, and that's all you have to do on this one. If you knew what that function was, you could only mess with your moment with respect to the x-axis. Because you know the moment with respect to the y-axis is 0. Okay, because it's the same thing on both sides. Now, if that was variable density, no, you have to then do all the work. Okay. But if it's symmetric with respect to the y-axis, it's on the y-axis. Okay, if it's symmetric with respect to any line, it's on that line. Okay. So that leads to the symmetry principle, which is here, which can make life much nicer at times. Okay? If a lamina, remember lamina is uniform plate, uniform density, is symmetric with respect to a line, any line, it doesn't have to be the y-axis or x-axis, but any line, then its centroid has to be on that line, without a doubt. Okay? And if you're dealing with lamina, remember we don't have to say center of mass anymore. You can say centroid. Don't say centroid. Okay. So, here's example 4. All right. Find the centroid of a circular half disk of radius 3. So here you have a circular half disk. This is half of a circle, a semisphere. Half a circle. I mean, not hemisphere. Semicircle. Semicircle. And what's the centroid of that now? It's a half disk. This picture is not too good because they didn't color it in. The one in your text has it colored in. When I first looked at this one, I thought they were saying the centroid of this wire that goes like this. Okay? That would also be here if it's uniform density wire, but it wouldn't be necessarily that. Okay? So this should color this in. And your book is blue. They have been doing sort of a beige color, but this is the disc, not the wire, not the surface of the disc. Okay? So this is your radius of 3. Find the centroid of that. We're assuming a uniform. Well, when they say centroid, that means laminar plane. Everything's equal density. So you know that's got to be on the y-axis. So x equals 0. X bar is equal to 0. It's got to be there. Okay. So now all we have to do is figure out what the y bar is. Okay. Now, how are we going to do that? Well, they gave you, lucky you, they didn't give it to you in the problem, but they gave it to you in the figure here, that this semicircle, let me shrink this down. If you do your dx's here, okay, this is going from this point here. What is that point here? What is the thing? Obviously, the x, okay, 2 things here. Because of symmetry, we can just do our area for sure as 0 to 3 and double it, right? So save ourselves a little grief there. What we have to do is figure out what's the height of this thing. That's where this thing comes in handy. If this is a semicircle of area of radius 3, circle of radius 3 would be x squared plus y squared is equal to 3 squared, right? Circle of radius 3 centered at the origin. So a semicircle would be half of that. So you only have the top half of that. And that would be, so what I just said, the whole circle would be x squared plus y squared is equal to 9. 3 squared, right? That's the circle center of the origin. If you only got the top half of that, then you've got the y, solve for y, and this would be y squared is equal to 9 minus x squared, right? And take the square root of that. Y is equal to positive square root of 9 minus x squared. So that's where that comes from, right? So that's the top half. So that's your y value anywhere there. So your height is this thing right here. And your width is your dx. Now, we don't care about distance from the y-axis. We know that's going to be 0. We're only caring about distance from the x-axis. Okay? Well, again, you'll use the midpoint, right? And the midpoint will be what? Half of this times that times dx, right? So that would be your m sub x. Would be 1/2 the integral of now. And what is your x going from? Okay, wait. Okay. can you double this too? I don't see why not. Let's try it and see if we get it. I see no reason not to just do 0 to 3 and double it. So if you double it, you wipe out the 1/2 then, right? Okay, so it'll be 0 to 3 of the square of that y, right? But y is the square root, so that's going to be 9 minus x squared dx. Is it going to come out that easy? It doesn't seem like that's fair for it to be that easy, does it? Let's see if it does. Okay? And what would this be? Antiderivative of 9. Second. 9x. Right? Differentiating. That's why I said antiderivative. Okay. Next. Minus x cubed over 3, evaluated from 0 to 3. What would that be? (27) minus 9 equal 18. Okay, I think this is way too simple. I'm not seeing where we get our pi's in here. Oh, I think I do know where we get our pi. Okay, let's continue with it. Then we need to do m, right? Okay. Now, here's where we cheat again. Okay. What is the mass? How do you know that? Maybe not. Okay. What is mass? Area. What's the area of a circle? What's the area of a semicircle? 1/2 pi r squared. Okay. So in the density we're assuming is 1, right? So our mass, we're going to be 1/2 pi, and what's our r in this case? 3 squared is 9, so this is 9 halves pi. So we didn't have to do integration there. We know what the area of the circle is and what the area of a semicircle is. So we don't have to do that. We can just use that. So now our y bar, we already know x bar is 0 from symmetry. Okay? So our y bar is this, 18 divided by 9 halves pi. Okay? Now, the 9 will go into 18 twice, right? Then flip the 2 over, and that gives you 4 over pi. And sure enough, that's exactly what we get. The y bar is equal to 4 over pi. Now, to get an idea of what that is, pi is about a little over 3, right? 3.14. So this would be 4/3, so a little more than 1 up here. Remember, this is 3. That would be 1.5, so it would be less than 1.5 and greater than 1. So closer to 1. Okay. And there, that looks pretty reasonable. because you've got mass above and below and around. So that actually came out far easier to do just because you can use geometry and you can use symmetry, right? And our assumption here that we could only do from 0 to 3, and that worked just as well and made it a lot easier. All right. The next example, how are we doing? Yo, yuck. Okay. This is sort of a bugaboo, okay? Now, we're using additivity and symmetry, but remember the centroids aren't additive, it's the moments are additive. Now, they gave us this way at the very beginning, and if you'll turn back a page, you'll see when it talks about lamina, if a region is decomposed, you see that italicized thing right under there. If a region is decomposed into smaller, non-overlapping regions, then the moment of the region is the sum of the moments of the smaller regions, not the centroids, okay? The moments. And then you have to still do the centroid, okay? So here we have a beautiful looking design here. You're going to do this in your engineering class, right? That looks like something that'll work really well, right? What? I'm not sure. Okay. What they're asking here, find the centroid of the region R shown here, and that's the entire region here. This time they colored it in properly. And what they show you here, you have a circle of radius, what? 2, okay? But it's offset up here. And what do you have down here? Okay, what kind of triangle? Not quite. This is, well, it may be. You may be right. No, I doubt it. Okay? Because this is 4 here. If that were 4, it would be somewhere up here. It looks like it might be equilateral, but it isn't because this height here is 3. So we can't say that it is equilateral. It's got to be isosceles. It could be equilateral, but I'm guessing not. Okay? So it's going to be an isosceles triangle there, a base 4, height 3, obviously, right? If it turns out being equilateral, fine, but I don't think so. Definitely isosceles, base 4, height 3, and then a circle of radius 2. Okay. So the moment of the region is the sum of the moments of the triangle and the circle. Okay. And we're saying this is a lamina, so can anyone guess what the x bar is going to be? 0. Okay. Got that part. Half of the problem's done, right? Okay. Half credit for doing almost nothing. Okay. But the second part here, we've got to deal with the moments, and then the moments we'll fiddle with. Okay? Now, all right. We saying it's a lamina, centroid, it said find this. Okay. The example said find the centroid, which implies by that verbiage that it's a lamina, uniform density, so we'll say the density is 1. Okay. Now, that's the first thing they do. It's symmetric, so we say x bar is 0. We've got that done. So to find the y bar, we do m sub x. Whoops. And I don't know if we're going to have time to finish this. Probably not. M sub x. Okay? Now, from back on the previous page, if a region is decomposed into smaller non-overlapping regions, this is, and the moment of the region is the sum of the moments of the smaller regions. So what we got to get is the moment with respect to the x-axis, okay, for this. What do you think the moment of the circle is here? We can do either one of them first. Which you want to do first, circle or Well, they do the circle first, so let's do it. What's the moment of the circle? Okay. Sure looks like it should be, shouldn't it? Okay. That's where the centroid of the circle is at 5. You're absolutely right. The centroid of the circle is at 5. So, Y bar for the circle is 5. Right? Now, what is Y bar? Is what? Yes, exactly. So, exactly. And you want to hazard a guess what M is? Okay, and what is R? 2 squared is? So, 4 pi is your denominator. Making great progress here. Okay? And this is your M sub x for the circle, right? But stop right there. That's what we're looking for, M sub x of the circle. So multiply both sides of this equation by 4 pi. So you get M sub x for the circle is equal to 20 pi. Right? Do you buy that? I mean, it almost seems too simple, doesn't it? Okay? We'll buy it. We'll take it, though. We'll take simple. Okay. Now what we have to do is find the moment for the triangle. Moment with respect to the x-axis of the triangle. We know it's y is 0. Okay, so we're okay there. So what we have to do is that part. So M sub x for the triangle. That's what we're working on now. Okay? So why don't we do this? Okay. What is the, let's do our dx there. What we have to do is come up with an equation for that line. So let's just do this one with double. So what's the equation for that line? Second? Okay, I like the way it's starting. Say that again. Okay, and what is it? Minus 3/2, right? It's going downhill, right? Down 3 for every 2 it goes over, right? Yeah, rise over run, fall over run, okay? That's the slope, x, plus 3. The y-intercept is 3, right? All right, there is your y, okay? So that's the height, okay? So your mx for the triangle is, your delta is 1. We're just going to assume that, get it out of the way. And then what is your mx here? Say again? Still couldn't hear. Integral, okay. All right. Good guess. Okay. So what? A dx. Okay, I like that. Second. It could be, unless you want to double it. Okay, so we'll put a 2 out here and go at 0 to 2. You okay with that? Okay. Second. Y. Okay, yeah, okay, I couldn't hear. Y. And the Y is negative 3/2 x plus 3. That's ugly, isn't it? Don't answer that question. Okay. Okay. Now, what you got right there is your mass, right? Isn't it? But we didn't. Ooh, wait. No. That is the mass right there. That's not the moment with respect to the x-axis, right? Because the mass is the length times the width times the integrated over. So that right there is exactly the mass. You want to go on and do that first, since you got it? So let's do that. So integrate that. In fact, what I would do is this. Integral from 0 to 2 of minus 3x plus 6 dx. I think I'd do it that way, wouldn't you? Okay. And what would that be? Perfect. Right? Is that right? Is that right? You okay with that? Okay. Which would be 6. That seems way too simple, doesn't it? Okay. That's one way you could do it, or we could have done the area is 1/2 the base times the height. Well, half of that is 6. So we could have done that much easier. But I just want to show you it works out both ways. Okay. That part up there is just the area. Okay. All right. What are we missing? What do we need otherwise? The what?
What are we missing?
Yeah. To the m sub x. See, I said when you got this far, I said, well, that's just the area. Okay? And we showed it's indeed just the area. Because of the mass. Yeah. That's it. Okay. What are we missing to get m sub x? Okay, density was 1. Okay. Taking care of that. Remember the midpoint? Remember the midpoint? You do that for each one of those. And what was the midpoint? Half of your y. So you would do a half, which wipes out the 2, and square that. Right? That's what we need to do. Okay? So this is the integral from 0 to 2 of, ugly but doable, what is it? I want you to tell me what to write. Yeah. Square that. 9 over 4 x squared minus, right, because you got a minus out front, right? Minus how about just 9x, because you double the cross term, right? Right? Okay? And plus 9. All right, I feel like a dentist. Okay. Okay. Now, I think we can integrate that, can't we? Hopefully. Please say yes. How? Second? Okay. Or let's make that 3/4 x cubed. Got it. Let's evaluate it from 0 to 2. All right. So I'm pretty sure that's going to be 8. 4 going to 2. That would be 6. Is that right? Minus. And that would be 4 divided by 2 is 2. 18. Right? Plus 18. I think just comes to be 6. Can you believe that? Did we wind up getting 6 again for our answer? Yep, that's it. Okay. So that's the moment with respect to x for the triangle. Moment with respect to x for the circle is 20 pi. So our total moment is the sum of those two, which is 20 pi plus 6 over, okay, that's the moment. Divide that by the mass over 6, and this will be, yuck. Oh, wait. Nope. Sorry. 6 was just the mass of the triangle. What was the mass of the circle? Plus 4 pi. Sorry, I forgot about that. 6 was the mass of the triangle. 6 was also the moment for the triangle. Strange but true. And so this gives us, and you can simplify that a little bit if you wanted to. That would be 2 times 10 pi plus 3 over 2 times 3 plus 2 pi. Okay. And 10 pi plus 3 divided by 3 plus 2 pi. It's going to give you the same answer it does in the book. And that's about 3.71. Did you already plug it in to see? I believe it. So, sort of a messy problem, okay? Looks sort of simple, but it can get a little complicated. All right, we ran over, but there's no extra charge. Okay, all right, so get freebie today. We'll begin next time with Okay. Boy, when they do this triangle, they really do a bizarre thing here. We didn't do it that way. We got the right answer. Okay. I don't know why they chose to do that. Well, they leave off the theory of Pappus. That's where we'll begin next time. Theorem of Pappus. And there won't be a slide for it, but then we'll do one little simple problem with it and go from there. All right. We almost finished 8.3. Homework exercises here. Do any of the odds 1 through 9. Any of the odds 11 through 17. Do 19. Do any of the odds 21 to 25. Do 27. Do either 29 or 31. Do either 33 or 35, or both if you choose. 37 or 39, or both. Okay? Okay. We'll wait and do 41 later. All right, good deal. Sorry we ran over. We'll pick up and go from there. Good deal. Any questions? Okay. End this.